Hello. In the last lecture, we tried to design microstep band pass filter and band reject filter. Then we saw how to do the parametric analysis if we want to change a particular parameter. After that, we tried to design a two-way equal power divider. So, this is the geometry of two-way equal power divider. This we tried to design in CST Microwave Studio on FR4 substrate, and then we saw the simulated results. So, let us go to the CST Microwave Studio. So, you see this is the geometry that we created in the last lecture of two-way power divider. We simulated this design to see its parameter, and then we saw when the output is given to port 2, the power at port 3 is very high. So, the isolation between these two ports is very less. This is what we saw in the last class. Now, if we want to improve the isolation between these two, what do we need to do? So, in order to do the isolation, if you go into theory or if you revise the previous lectures, we need to attach a resistor which should provide me the isolation. So, in case of two-way equal power divider, we should attach a resistor between these two ports. The value of the resistor should be 100 ohm. So, in this case, since we are working at 900 megahertz, we will use the SMD resistor, and the size of the SMD resistor is very less. So, in our case we will be using 0603 SMD resistor. So, we should make the pads accordingly. Now, just to show you the results of two-way power divider, if you see here, so if you see S12 and S31, this is minus 3. However, if you see minus 32, this is minus 6 dB. So, the isolation is very less. Now, suppose if you have made this geometry and if you are not worried about the isolation between these two ports, and if you just simply want to fabricate this particular PCB. So, what do you need to do? You need to just simply select this. So, to select this, select the face in which you have made the geometry, then align your WCS with this face. So, we have aligned here. Now, if you want to fabricate this particular PCB, all you need to do is you need to export it in Gerber format. So, I will show you how to export in Gerber format. Right now, I have aligned my local coordinate system with the upper layer of this particular PCB. So, then if you go to export and then select 2D option, here you have a Gerber format. Now, if you want to use other formats, you can select the appropriate format. In most of the fabrication lab, we need to give Gerber file. So, that is why we will be exporting it in Gerber format. So, just select it. So, you can here select the appropriate folder where you want to create the Gerber file of your geometry, and you can name it as per your requirement. So, maybe I will just give the name as top. So, it will create the Gerber file. All you need to give is you need to just give that Gerber file to the manufacturer, and you need to tell about the substrate and the substrate size, and you need to give the dimension, and you need to tell them that it is a double sided PCB. So, he will fabricate your PCB. So, this is regarding the fabrication process. Now, if you want to use this particular geometry as a combiner also. So, what you need to do? You need to provide a resistor between these two, and to connect the resistor we should provide the pads accordingly. So, just to make the geometry of pads, I will just select this layer, I will select this edge, and then I will align WCS with this, and then I will make a strip between these two. Just to show you the geometry, here this is the geometry of power combiner. If you see here, rest of the geometry whatever you see, it is similar to the previous design, but in between you can see here one resistor is there. The size of this resistor is 0603. So, 0603 resistor will be soldered on the pads. So, we need to make the pads to solder this particular resistor. So, here we will be making the pads. So, go to CST again and try to make these pads. So, we will simply create a brick. So, to create a brick, again go to brick and maybe write it as pad. Then in U, here you need to just ensure that this line should be 50 ohm line. So, again the width of this should be corresponding to 50 ohm. And so, V here will be nothing but 2 into So, we have created one strip. The thickness of this strip will be same as the copper thickness. So, T, and the material will be PEC. So, now we have created a pad. So, this is a strip. Now, here there should be some portion which should be cut, because we want to place a resistor here and then we want to solder at these two ends. So, at the center, just select the center of this particular layer and then align WCS with that, and then you cut a strip of this size. You select the size as per your resistor size. So, in our case, this resistor that we will be using is 0603. So, for 0603 resistor, the length is 1.6 mm and the width is 0.8 mm. So, accordingly I will cut the patch from this micro strip pad. So, in U, length will be same, and then V, maybe just take the variable name LSMD by 2. Sorry. Yes, and for thickness maybe minus T comma 0. Yes. So, here maybe just take it 1.6 or maybe 1.2, whatever you want. So, just to make the connection. So, we have created this step. Now, we need to just cut this from the pad. So, you can see here, just select this pad, go to boolean, subtract, and then subtract this cut. Now, you can see you have created this space. Now, what do you need to do? You need to just simply connect the resistor in between. So, just to connect the resistor, you just select this edge. Similarly, you select second edge and then go to simulation and select this lumped component option. In the lumped component, you can see here you can rename your component as per your requirement. So, I will rename it as resistor and I will give the value as 100 ohm. Okay. So, now you can see here, if you go into navigation tree, one component of resistor has been created. So, now my geometry is like this. Now, we have created the geometry. Now, we should see the performance, and to see the performance, just again start the simulation, go to simulation, or then start frequency setup solver and then start the simulation. In this case, what we are expecting? We are expecting that the isolation between these two ports should be very high. So, the power from port to port through port to port 3 should be very less. So, we will see results, just wait for the simulation, just wait for some time. Now, if you see in this file, so in this particular case, now if you see, this is the geometry for the combiner. This is the geometry corresponding to our dimension. Now, if you see the results, simulated results, here if you see, this is my S11, this is S12, that is Now if you put the marker, put here marker, if you see S21 value is minus 3.24, S31 value is minus 3.23. So it is approximately same as it was in case of two-way power divider without resistor. Now if you try to observe S32, see this value. So this value is very less. However, in earlier case it was minus 6 dB. So the isolation between port 2 and port 3 is very less. Now if you give the input power at port 2 and port 3, then you can get the sum of these power at port 1. So in this way you can design the power combiner. Now again, if you want to fabricate this particular PCB, use the similar procedure, just select this layer and then export it in Gerber form and then give it to manufacturer. So just to compare, I have just fabricated these PCBs. I showed you the PCB of these two power divider and combiners. Now I will just show you the measured results of power divider and combiner. If you see here in this is the geometry of two-way power divider. I measured these results. Here if you see, this is S21 and S31. So the power level is around minus 3 dB, and however if you see S23, so this brown color line is S23, so this level is very high because the isolation between those two ports, port 2 and 3 is very high. So that is why this level is very high. However, if you see S11 it is fairly matched in this particular frequency range. Then we made the power combiner. To make the power combiner, we use the SMD resistor. So this is the geometry for two-way power combiner, and then we measured this using network analyzer. So in this case you need to have at least 2 port network analyzer. All you need to give is, you need to give power at one port and you need to measure from other port. So if you have two-way power divider, you simply connect one cable here and another port over here and then terminate this with 50 ohm. If you have three-way power divider, then you give power from here and observe at these two ports. So if you see the measured results of this power combiner, here you can see in this particular case the S31 and S21 is minus 3 dB and S23, that is the isolation between port 2 and 3 is very good as compared to the previous case. It is below minus 15 dB for our desired range, even you can say below minus 20 dB also. So in this way we designed power combiner. In the next lecture we will try to design hybrid coupler. Now we will try to design hybrid coupler, that is rat race coupler. We will try to design the rat race coupler at 1.8 gigahertz. So this is the geometry of rat race coupler. It is also designed on FR4 substrate for 0.8 mm thickness. So here this is rat race coupler. All these sections are lambda by 4 sections and this section is 3 lambda by 4 sections. Now if you recall the basic theory of rat race coupler, so this line length is 3 lambda by 2. If you see the electrical separation between these, so this is lambda by 4, lambda by 4, lambda by 4, so this is 90 degree. However, if you see spatial separation, so they are separated by 60 degree. Now we will try to design this hybrid coupler in our CST microwave studio. So let's start again CST, create a new file. And repeat the same procedure. So this hybrid coupler we are designing at 1.8 gigahertz. So maybe take the frequency range from 1.2 to 2.5 gigahertz. So in order to design this, since it is a circular geometry, we will take the substrate of circular geometry only. So to design circular substrate, go to in modeling, go to cylinder and then escape, maybe name it as again substrate, write it as R sub, then Z is H sub, Okay. Take R sub as 38 mm, H sub as 0.8 mm. So, just to tell you, here the dimensions that we are taking for this hybrid, we are taking FR4 substrate of 0.8 mm thickness, we are taking the inner radius as 22.4 mm and outer radius as 23.2 mm. These things you can easily calculate using the line calculator. You know this electrical length and you know this periphery, that is equals to 2 pi r, and electrical length is 3 lambda by 2. So, that will be equivalent to 540 degree. So, you can use simple line calculator and from there you can calculate the inner and outer radius. Here the stub width is 0.8 mm, that corresponds to 70.7 ohm. How does this come? For that you can refer the theory of rat race coupler. This particular impedance calculation was told to you in the previous lectures. So, we will just simulate this geometry here. So, now if you see here, this has created the circular section. Here you can define the number of segments. I will take it as maybe variable again, we will define the number of segments. Let us take it as 36, and the substrate again FR4 substrate, select it from the library option, load. So, this is FR4 substrate. So, we have created the FR4 substrate. Now, to make the radial circular stub, enable first local coordinate system, align it with the top face, okay, and on the back side, as I told you, we need to make the ground. So, you can make the ground. So, just to do that, select the other face and again use that extrude option and then name it as ground and give the thickness as you use it for copper, that is 35 micron. So far we have made the ground and the copper. So, for the ground the substrate should be chosen as PEC substrate. So, mistakenly if you select any other substrate you can change it from this option. Now, on the top side again you draw a radial stub. For radial stub what do you need to do? You need to just again go to cylinder, escape, radial, okay. Then you name it as R out, then R in 0 T, and again the number of segments keep it as N, that is 36. So, R out take it as 23.2, I do not recall, just to recall I think it is 22.4 and 23.2. So, this is R out is 23.2 and R in is 22.4. So, substrate for this is PEC. So, now we have created the radial stub. Okay. Now, to make port, all you need to do is just go to view option, yes. So, select this particular segment substrate, yes, select a segment. To select a segment, select a particular edge, maybe this one, align your WCS with edge. Now, you need to define a port. So, to define a port again go to brick and then maybe name it as out 1, and this port should come up to this particular point. So, to define it, you know this separation is how much? This is R sub minus R in. So, we will take it accordingly. So, in V coordinates what you should give? R sub minus R in plus some extra length, just to ensure that there is a connection between radial stub and the output port, and thickness T, and in U this should be minus W50 by 2, W50 by 2, and W50 will be 1.55, and X maybe take 0.3. So here this you need to take in negative because positive is on the other side. This should be R sub, yes, we take this as 0.2. Now, what do you need to do? You need to just first with this particular face align your local coordinate system, and then you rotate these faces by 60 degree. So, to rotate it, select this out, transform, then rotate and copy. Here you give 60 degree, okay. And since you want to make 3 other ports, so you can increase the repetition factor. You can see here, right. So, you see we have created 4 ports. So, this is the geometry corresponding to our requirement, okay. Next we need to make the ports. So, to make ports, all you need to do is again replicate the same procedure, select this particular edge, yes, then define waveguide port and use the same procedure as we told you earlier, 3 into H sub and this 4 into H substrate. So, this is how you create a port, and then you can rotate this port again. So, transform to rotate it, select rotate, select minus 60 and copy. You see, you can simply create these number of ports. Now, if you see, this is the geometry. Now, we have created all the ports 1, 2, 3, 4s. Now, we need to simulate. So, to simulate it again, you need to give all the background properties, boundary conditions and the frequency range. For that, go to simulation, define frequency range. Since we have already given the frequency range, we need not to define it again. Then you select the boundary properties, open add space. If that is already not enabled, you need to apply it in all the directions, and then start frequency setup solver. Start the simulation and then wait for the results. So, it just takes some time. So, meanwhile, we will discuss what we are expecting from our simulation. So, now if you give input at this particular port, this length will be 5 lambda by 4 and this will be lambda by 4. So, power here will be in same phase. Now, if you see at this particular port, this length is lambda by 2 and this length is lambda. So, they are in phase reversal. So, the phase difference between these two is 180 degree. So, here at this particular port the power will be in opposite phase, so it will cancel out. So, ideally the power at this port should be 0. Now, if you see at this particular port, this length is 3 lambda by 4, again this length is 3 lambda by 4. So, again here the power should be half and it should be in same phase. Now, if you compare these two ports, so here it will be shifted by 90 degree and in this case it will be shifted by minus 270 degree. So, we will try to observe this in our simulation result. Now, just go to simulation result. So, the simulation is still going on. So, in between I will just show again, if you want to fabricate this particular design, you export the geometry in Gerber format. You see this is the fabricated PCB. Now, again just to measure it, you give input at one port. If you have 2-port network analyzer, then you connect the other port at any of these outputs and other 2 ports should be terminated with 50 ohm. And the similar way you can do the measurement for all the ports. So, these are the measured results for this geometry. You can see here this is S11 black one, this line is S11, this blue one is S22 and this red curve is S33. So, this was designed for 1.8 gigahertz and for S13, as I told you, that is isolated port. So, you can see S13, the isolation is very high at this particular port. So, the power going to that particular port is very less. Similarly, if you feed at port 4, that is port 4, let us take maybe this as port 4, then the power at port 2 will be very low. So, you can see S24, that is this one, this is very low. So, in this way you can design a hybrid coupler. Now, just to see the simulated results here, so these are the simulated results. In the red line you can see that this is the S11 curve, the green one is the S21 curve. So, at port 2 the power should be minus 3 dB. Similarly, at port 4 the power should be minus 3 dB. So, S21 and S41 both are minus 3 dB, wherever S31 is very less, so it should be well below minus 20 or minus 30 dB, which will show that this port is isolated. So, in this way we will simulate the hybrid coupler. So, in this particular lecture we tried to design the power combiner and then we tried to put the SMD resistor component between the 2 ports and then we saw the performance of power combiner and we saw that the power from port 2 to port 3 is very less. So, these 2 ports, if we feed the power from the 2 output ports of power divider, then the power can be combined and the combined power can be observed at the port 1. After that, we tried to design the hybrid coupler, 4-way rat race hybrid coupler, and then we saw the performance. If we feed the power from one port, what will be the power at other port. Now, just to highlight one more thing, if we give power from port 1 and port 3, by using the same concept, here we should get the sum of these power and here we should get the difference of these powers. So, by using these same concept, you can do the simulation. Just to excite these ports, you need to just give power here and at this particular port and just give the amplitude 0 at these 2 ports and you can easily verify the concept of hybrid coupler. So, in the next lecture, we will try to do the simulation of active circuits using CST Microwave Studio. So, for this lecture, thank you very much. We will see you in the next lecture.